Hello everyone. Today I will present my paper named Semi-supervised Segmentation of Histopathology Images with Noise-Aware Topological Consistency. Our main task is to segment the glands or nuclei from the pathology images. The input is the pathology image and the output is the binary mask. Accurate segmentation is important because it can be the basis of diagnosis and it can facilitate survival prediction. On the left side, you can see the tubular adenoma has not that distorted glands, while tubular villus adenoma has very distorted glands. Then, accurate segmentation of the glands can help us to determine if the patient has lower risk or higher risk to colon cancer. Also, on the right side, you can see the orientations of the nuclei has something related to the survival time. So if we can accurate the nuclei very clearly, then we can determine the orientations to be consistent. And then we can decide whether the patient is in long-time survival or short-time survival. However, the problem of the accurate segmentation lies in the limited availability of labeled histopathology data, because you need to annotate and detects the boundaries of each gland and nuclei very carefully. So the annotation burden is really heavy. Also, it needs domain expertise to annotate this kind of data. That's why we need semi-supervised methods, using small group of labeled data with large group of unlabeled data to train the model. One main scheme in semi-supervised methods is consistency-based regularization methods. The main idea is to enforce consistent predictions under different data augmentations. One main framework is mean-teacher framework. The student and teacher model has the same architectures, and the teacher model's parameters is updated via exponential average of the student model. Current consistency-based semi-supervised methods mainly focus on per-pixel or voxel consistency. They fail to learn the topological characteristics from the unlabeled data. In consequence, they cannot fix the structural errors, such as roundly merging glands or nuclei. Existing methods such as XNet cannot fix the locations prone to topological errors. They may conduct false positive predicted glands. Also, they may have false negative holes inside the glands. So our approach is proposed to target these issues. The main intuition is that under different perturbations, the topology of the outputs should be consistent. So our approach is to enforce the topological consistency between noisy topological features. Given the student and teacher likelihood maps, we firstly captured the topological structures using percent diagrams. Then we formulate the noise-aware topological consistency laws between these two diagrams. However, directly matching between the two noisy diagrams is not that effective, because we don't want the matching between noisy structures. So decomposition strategy is proposed to avoid directly matching between noisy structures. This helped the model to learn the robust topological representations from the unlabeled data. Also, after decomposing the person diagram into signal and noisy parts, we enforce the signal consistency and remove the noise. Also, our method is backbone agnostic and stable to small perturbations, such as different data augmentation strategies. Here are some qualitative results. As you can see here, our methods can separate the glands and the nuclei very clearly. And also, our methods can remove those false positive predicted glands or nuclei. From the quantitative perspective, we evaluate our method not only in pixel-wise but also on topology-wise. Our method has achieved the highest performance across all evaluation metrics, especially in topology-wise. This means that our methods can greatly reduce the topological errors. Thank you for listening, and thank you for all my collaborators. This is the link and QR code to the code implementation. And if you have any questions, please feel free to contact me. Thank you.